Okay, second speaker is also from Oxford. It's Agnes Luscher, who's a student of James Sparks, and she'll talk about localizing punctures in M theory, which is a paper that appeared this morning at the archive.
Yeah, so it's a very recent work in collaboration with Chris and James. So the punchline of it is that we obtained the central charge of some filters that are compactified on some puncture Riemann surface. And the way we obtain it is by looking at the supergravity dual and using equivalent localization. That's the big message. So there are lots of keywords in what I just said, so I'll decompose that throughout the talk. So first I'll give you some motivation of our setup and then review briefly equivalent localization, then tell you the holographic dual we're looking at. And this last part will get you adding punctures to the setup, which is really our contribution. So I'm looking at a stack of M5 brains, and note that I can take two perspectives on those brains. So on one hand, I have the word volume theory, which is just some 6D 2,0 field theory. Or I can go to the holographic tool, I get the near horizon of the brains, and that looks like ATS 7 times S4. So now what I want to do is to compactify or wrap my brains on a possibly punctured Riemann surface. And so now the word volume theory is four-dimensional, can be obtained from the 6D 2,0 wrapped on this Riemann surface. And this is a very rich class of field theories, which are generically quite difficult to study. So they're not Lagrangian, but they're very interesting. And so we want to start them by going to the holographic dual, which is in the New Horizon geometry, just ATS5 times M6, where my internal space is a sphere bundle over the Riemann surface. So the sphere is the one that was present before with the ATS7, and now it's fibers over the Riemann surface I added in. So what we do is study the supergravity, and we can compute observables there, and that translates to observables in the field theory. And so we're going to be computing the central charge, and in particular, what's the central charge when there is puncture on the Riemann surface. So the tools we're using is equivalent localization. So that's a method to compute integrals where you have a space with a symmetry, and in particular, you don't need to know a supergravity solution explicitly to be able to use that method. So that's very powerful, and I'm going to review how that works. So I consider a space with a symmetry, generally a U1 symmetry, and I can associate a Killing vector, call it Xi, and out of that vector, I built this object called equivalent exterior derivative. So it's just a usual exterior derivative to which I add a contraction with the Killing vector. So as the exterior derivative raises, the degree of form by 1, contracting lowers the degree of form by 1. This object naturally acts on things that are called polyforms, so it's just a form composed of forms of different degrees. And the type of polyforms I'm interested in today are the ones which are called equivalently closed. So when I act with the Xi, I get 0. So order by order, that means that the top form parts phi n is closed, and then sine phi n is d phi n minus 2, and all the way down to sine phi 2 is d phi 0. So if this series of equalities realized, I call the full polyform equivalently closed. Why am I telling you about this? It's because I have this math theorem that tells me that if I'm now trying to integrate that polyform, its top form part, rather than having to do this big integral, n-dimensional integral, I'm just going to pick up scalar contributions from the 0 form part of the polyform. So you just need to evaluate that scalar thing at some special points. And these special points are the one where the symmetry acts trivially. So if you think about the sphere, for example, the U1 is rotating your sphere, and the poles are fixed under the action of that rotation. So that would be my fixed point. So rather than doing an integral over the full sphere, we just evaluate that phi 0 on the two poles. So that sounds good. The BI's are just the weights of my symmetry action. So I can decompose my Killing vector, and the BI's are just the coefficients of this linear decomposition. So that's a bit simplified because I can actually have higher dimensional subspaces that are fixed under the action of the symmetry. So for example, I can have fixed surfaces, and so I would pick up additional contributions to my integrals. So given by still integrating over this fixed dimensional subspace, dimensional fixed surfaces, sorry. And the way to evaluate these contributions now use the two-form part of my polyform and still the phi zero. I don't really need the details of this formula for that talk, so I'm going to hide it now. What I really want you to take away to keep following is that rather than doing this n-dimensional integral, I can reduce it to some fixed point, so zero-dimensional contribution that I'm going to refer to as knots, or some fixed surfaces contribution that I refer to as bolts. And I can evaluate these contributions if I know the zero form and two form parts of my polyform. And in particular, now I do these integrals without knowing the explicit supergravity solution. So that's really what makes it cool to use and what makes it different. So where do we want to apply equivariant localization? So I mentioned that we want to look at ATS5 times M6 supergravity solutions. And we want to be computing the central charge, which is just the integral of the full internal space with a lambda is just a warp factor. And we will also want to be computing some fluxes, which are just the integral of the four-form flux over some 4 cycles in my internal space. And we're lucky enough that my collaborators, thank you, Jerome, built this equivalent completion for these observables that we want to look at. So they gave us what phi2, phi0 were that we want to put in the localization formula. And they're actually not very mysterious. They take this form where y is just a coordinate on my internal space. That just denotes where my fixed point is in the internal space. That's going to come again in my formula later. And the omega is a killer form, but this one we're not going to see anymore. So I can just use these, plug them in the localization, and get results. So let me review first the smooth Riemann surface before adding punctures. So they studied that example in the same paper where they built the polyforms. So the topology of my internal space is this sphere bundle over the Riemann surface. So the S4 is fibered with some vibration number P1 and P2. And I want my total space to be Calabi-Yau to preserve inverse symmetry. And so the P1 and P2 need to sum to the Euler number of the Riemann surface. That's just this first constraint. And then I have my U1 action that just rotates the four spheres. So these phi1, phi2, they rotate the two complex I bundles with this weight P1, P2. And say I rotate the sphere, the action's fixed at the two poles. What's fixed there? Well, that's the full Riemann surface. So my fixed point set consists of copies of the Riemann surface at the two poles of the sphere. So that's exactly these surface contributions or poles contributions. I can go ahead, use the polyforms, plug everything in the localization formula, and they obtain that result that matches the explicit construction of these people. And importantly, that is an off-shell result. So what do I mean by off-shell? That we would still need to extremise over these B1 and B2 parameters under the constraints. And that would actually impose the equation of motion and put you on shell. And that's really the supergravity manifestation of this thing called A maximization in field theory that makes you extremise over the R symmetry. And that makes sense because this psi is dual to the R symmetry vector in field theory. So that's really mirroring that process. Just wanted to mention that that was n equals 1 setup. I can also enhance supersymmetry if I trivialize one of my direction. So I just turn off one of my flux, and then that changes my central charge to what was obtained by Maldacena and Nunes for this more supersymmetric setups. So now we can add punctures to the setup. So we want to do that now with a Riemann surface that has punctures. And a key feature of the central charge of this theory is that it decomposes into a contribution that is just a smooth Riemann contribution, and then a sum of contributions just at the punctures. So we can study the punctures individually rather than tackling the full punctured Riemann surface. So in the following, I just want to tell you how to obtain a single puncture contribution, and you'll have to keep in mind that then you can just reinsert it to get the full punctured Riemann surface central charge. So what do I mean by a puncture? So I mean that I go to a point on my Riemann surface, and that's actually an orbifold point, or actually some resolution of some orbifold. So what do I mean by just orbifolds? C mod zk. So if I just had like a smooth point in the complex plane, I go around, I pick up a phase of 2 pi. Now, if I have a quotient, an orbifold point there, I go around the point, I pick up a phase of 2 pi over k. So I have this deficit angle. Okay, so that's just a normal C mod zk point. But now I have to remember that my Riemann surface is actually part of this 6-dimensional internal space. So when I quotient at this puncture, I'm also quotienting in the other 2 complex directions. So I actually have some C3 mod zk locally, not just C. And so the way I act, I have 2 pi over k on my Riemann surface direction, and then the 2 line bundles, the quotient acts also with these weights alpha 1 and alpha 2. And then what I mean by resolving, to just give you a very schematic picture of it, so I can think of my orbifold point as some kind of edge, and then I can kind of cut the edge to make it a bit smoother, and that's what I call resolving. That's kind of schematic, but maybe that's helpful for you to picture what's happening in a second. So before even resolving, I can already obtain a result quite easily of just what happens if I just put this C3 mod zk quotient. I can actually run through the same procedure I showed you for the smooth Riemann surface, but now these these flux numbers p's, are shifted by these alphas. So like the quotient acts as kind of shifting my vibration number. And so everything I was telling you for the smooth Riemann surface still holds, but for these shifted fluxes. And so I will just obtain a shift to the central charge proportional to these alphas. And that's already a result that wasn't in the literature. And that really comes out of doing nothing more than what was already there. But now if we want to start resolving the quotient and get some new, more interesting kind of punctures, then you need to introduce more tools. And that's what I want to get to. So because it's a bit more difficult, not much, but we're going to start with n equals 2 puncture. So again, I turn off one of my directions. So just pick like the quotient to not act along one of the direction. And that enhances the supersymmetry to n equals 2. And I'm just considering C2 mod zk quotient, so slightly smaller geometries. And so I can draw the toric diagram for C2 mod zk. So C2 has a U1 squared action. And the toric diagram is the 2 lines where each of the U1 shrink. And what I do now is to resolve. So that's where I introduce my kind of plane that cuts my edge. And so that's the toric diagram now for a partially resolved C2 mod zk singularity. So now I want to see my puncture as having this toric geometry at the point of the puncture. So I play it in, and in terms of localization, I have a bunch of orbifold points, some fixed points that has orbifold number, this little k. And the last of the fixed points is actually a fixed surface, so that's going to be a volt. And I glue it in on my Riemann surface around in the neighborhood of that point. And so this dashed line is kind of where my toric geometry meets my Riemann surface. So now I can go ahead to localization. The first thing I want to do is to quantize some fluxes. So each vertex on the toric diagram represents a cycle. So I can quantize fluxes through these cycles. In terms of localization, I pick up some fixed points on each side. And these fixed points are characterized by these y's that were like their direction, their position in the internal space. So I told you the y would play a role. So they appear here. They characterize where the fixed point is. And the detail of the relation is not too important. What we need to know is rather than talking in terms of y, I can talk in terms of fluxes. So to each of these points, I associate a flux, little n. And so I can just use that as my new set of variables, this little n. And that's relevant because the last of my flux is capital N, which is my number of M5 branes and the parameter that defines my field theory. And this capital N through my flux quantization can be expressed as just the sum of this k orbifold number and this little flux, little n. So what I'm telling you is that these 2 sets of parameters define a partition of n. But that's a well-known fact in field theory that you can characterize n equals 2 punctures in terms of some partition of n, or also in terms of a Young tableau. So when you want to give me a puncture, you can also just give me a Young tableau, and that gives me all the information about your puncture. So that's something people already knew in field theory, and that just comes out of quantizing the fluxes in our procedure. So that's quite neat. And so now we can go ahead and compute the central charge. I'm going to pick up a bunch of knot contribution, 1 bolt contribution in my localization formula. The explicit form is not too important. I can evaluate all of the terms in terms of this data in this Young tableau, and that recovers some field theory results, also some supergravity results. So here we're not producing much new, but what's really new is the way we're obtaining it. And in particular, as I was already saying, we don't need this explicit supergravity solution, whereas these other people needed the explicit solution. And so now our approach generalizes to n equals 1 puncture, where like other people weren't able to approach this n equals 1 setup. So just wanted to mention that this formula is scary looking, but it's actually very explicit. Just pick a Young tableau, put the parameters in. It looks actually really easy. You just need to specify what you're looking at. So nothing scary going on. So let's turn to n equals 1. So we were looking at C2 mod zk, now this is C3 mod zk. I have this additional dimension. So I again just have a toric diagram, but with one more direction. So now I'm in 3D. And again, I can resolve by adding these planes. The story is exactly the same, but in 3D. So I'm going to pick up again a bunch of fixed points and 1 bolt. And so I can again just do localization with a bunch of fixed points and 1 bolt. And so I find a very similar formula. So that's the puncture contribution to the central charge for n equals 1. The bolt contribution looks a lot like the orbifold one with the alpha 1, alpha 2. There are a few more parameters, so that's a bit long to put on the slides, but that's really not much else entering. And so that's the result. So a few comments about it is that whereas in the n equals 2 case, you're giving me this Young tableau, and I could evaluate everything that was entering in the central charge. The situation in the n equals 1 is a bit different. So in particular, I don't have a 1-to-1 correspondence between my fluxes and these y's that are the positions of my fixed points. So I still have some relations between the fluxes and the y. So this is just this linear relation. I can still quantize the fluxes. And now I can put them in, I can insert them in my results. And that will still leave some y's that are not specified in terms of the fluxes. But in particular, that will give me something that is a cubic polynomials in the b's and also a cubic polynomial in the y. But that is exactly what you would expect to find from the field theory perspective in terms of a maximization. You expect to find something that is cubic in the parameter that you want to extremize over. So it's really cool for a result because it really takes the form that we expect people are going to be able to match from the field theory side, so that this off-shell central charge, people may obtain something that has really like the same structure. And so we're hopeful for that. And then you should still extremize. So as I'm mentioning, the PI you can only extremize over when you put it back in the total central charge. So you need to take into account all the punctures to do this extremization. But you can extremize over the y's, just that expression that's on the slide. And when you extremize over the y's, you get a bunch of quadratic constraints that exactly corresponds to imposing the equation of motion for your flux. So again, this extremization is a kind of partial off-shell procedure. So that's, again, quite cool. So let me just wrap up. So I showed you how to obtain this little delta A, so the puncture contribution to the central charge. So now you have to remember to put them back in the total central charge to have the central charge with the puncture agreement surface. And so in particular, our method relies on the use of equivalent localization, which circumvents the need for an explicit solution. So for n equals 2, we just recover what was already in the literature, but in this really straightforward way, which also generalizes easily to n equals 1 puncture, where we really obtain completely new results that we're hoping for people to go ahead and match. So in this talk, I focused on M theory and this ADS 5 times M6, but you can do that also in type 2B that should come out next week. And also in more setups. So that you could also imagine not even using punctured Riemann surfaces, but just orbifold geometries more generally, and resolving orbifold geometries or formalism should work there. And we're hoping to do that. So thank you.
Hey, thanks for a nice talk. Questions?
So I have a question. When you are trying to find the equivariantly closed forms, the Killing vector is on input. But if you don't know the metric, I guess you don't really know what's the Killing vector. So the question is this related to the fact that you have to do this A maximization procedure at the end of the story? Or how does this work?
So that's related though. So the way you would build this polyform without knowing the Killing vector is through like the Killing spin of bilinears, and the Killing vector is dual to one of these bilinears. So that's how you get like some relations without knowing explicitly your Killing vector. But then yeah, the maximization would fix the Killing vector in that sense. That kind of fun.
Any other questions? So there are other ways of getting 40n equals to 1 SDFTs, which is you start with 61,0 and put on a Riemann surface, and it's a little less systematic. But are there ways you could implement it there for solutions that are massive to I can't.
Yeah, we can do that as well. It's kind of quotienting the S4 in the internal space for ours.
But this is a special case. I'm talking about more generic 61,0 solutions, which were, I think, constructed. I forget.
Yeah, I think the same kind of formalism. I mean, maybe you need kind of polyforms in 2A, as you're mentioning, but I mean, I think we even have them. So you can definitely do the same thing. Like that's yeah, that's very like
geometry, odd-dimensional. Yeah, this is fine.
Yeah, so
It's more difficult, but it's
your bridge just need like these toric kind of tangents. Isn't it very that you should get one of it?
Yeah. Any more questions? Yes.
Do you think all of these resolutions will have a supergravity solution? So in the n equals 2 case, they do, don't they? The n equals 1? Yeah.
And that's a bit like the philosophy we think, like if the solution exists, that's what will happen. But
yeah, I
think they do though. I think they are expected to. I don't know the underlying arguments, but I think we do expect them to happen.
Ciao.
I got that. So here, when you are presenting how you do things, how you do the resolution and so on, it depends on this alpha 1, alpha 2, depends. That's how you get n equals 1 or equals 2. I guess my question is like, once you resolve these things, you know what kind of geometry you have, right? So why is it that you don't know the supergravity solution exactly? It's just that you cannot solve the equations exactly.
Yeah, you know the topology of your solution, but you're not writing down like an explicit like metric and blocks, like you just know that. Yeah, the topology.
So you only go for the spinners. You only need to go on shell partly, no? Somehow. This is the story, I think, no? And then I'm wondering, do you think constructing such bilinears and these polyforms might be simpler to find the 1/n correction than to actually construct the higher derivative correction in 11 dimensions, or it's equally complicated?
Hey, now we're getting political.
I don't know enough about the difficulty of the other method to have a good answer.
Probably pragmatic on that. No questions. So Neil, what do we do next?
Lunch.
Okay, lunch. But where's lunch? We go. Oh, it's here. Okay, it should be right there. Let's thank Alice again.